The last day of the conference, so it's a pleasure to introduce Pedro Salomao from the University of São Paulo. He's going to talk about three foliations in Hamiltonian dynamics near critical energy levels.
So, thank you, Sylvia. Thank you very much for the invitation. So I'll talk about, in fact, a work in progress with Nayara De Paulo and Umberto Inievich. And before I explain 3-to-3 foliations, I will start with the setup. So we have a four-dimensional symplectic manifold. And a Hamiltonian, autonomous Hamiltonian function, and consider the Hamiltonian vector field, the Hamiltonian flow. And so let's denote by WE the energy level at energy E, which is preserved by the Hamiltonian flow. So we assume the following situation, that for energy below zero, we find that WE has two components. Let's call it SE and SE prime. Then for energy equal to zero, these two components touch each other. They develop a singularity, and they touch each other. And for energy slightly above zero, then we assume that this is a non-degenerate critical point of the Hamiltonian function with Morse index 1. And so for energy slightly above, we have this one handle attachment, and the energy level looks like that. So this would be WE. So let me denote here S0 and S0 prime. So this is essentially the setup, and we want to address the following question. Suppose that you know some information about this energy level here, the critical one, and we want to see if we can say something about the energy level is slightly above zero. So let me say a little bit more about this critical point. So let's denote it by P. So this is a critical point of the Hamiltonian function. It's a rest point of the Hamiltonian flow. And we assume that locally, so let's take symplectic coordinates. Near P, and we assume that the Hamiltonian function near P has the following form. So this is the quadratic part of the Hamiltonian function. These are the higher order terms. And here up to some, we could put some positive constants here. Doesn't change too much. So let's look at the linear part of this Hamiltonian, just to understand a little bit more about the behavior of the Hamiltonian flow near this equilibrium point. So the Hamilton's equation are given by this set of differential equations. And the flow decouples as a saddle in the Q1, P1 plane and as a center in the P2 plane. So in this case, P is equal is the origin. And for that reason, this equilibrium point is called a saddle center. Equilibrium point. So let's look at the energy levels. They project in the following way. I just project the energy level to this plane. It's very easy to see this connected sum, the behavior of the connected sum in these coordinates. It's for E negative. It looks, the projection close to this point looks like that. For E equal to 0, the projection is these two quadrants. And for E positive, the projection is like that. So here we see that when we pass energy equal to 0, there is a connected sum of these two components. So for energies above 0, we have this point here. And so this point corresponds to a periodic orbit that we can see in this other plane, which is like that. So for each value of the energy, there is a periodic orbit that we see here. So this is for positive energies. Corresponds to this point here. If we take this diagonal here, which corresponds to here, let's say. So this part, so these points in this projection correspond to the disk here. So for each point here, there is a circle, and when you vary from here to here, these circles goes to 0, shrinks. And if you are here below, it's the same thing. So when you move the point here, the corresponding points in this plane at that energy level corresponds to a disk, shrinks to the. So this slice here corresponds to a two-sphere, the belt sphere, with this periodic orbit, which is the Lyapunov orbit, which is hyperbolic inside that energy level. And these two hemispheres, one of them in the interior is pointing to one of the sides, and the other one is pointing to the other side. So it's something like this two sphere is separating, it's here, it's separating the two sides of the energy level. And so there are orbits which are going from one side to the other, and in the same way. Okay. So let me state one theorem, a previous theorem that motivated this one that I will talk about today, which is a theorem by De Paulo and myself. 2013, which says the following. Suppose now, inside this setup, that our symplectic manifold is R4. With the standard symplectic form. Suppose also that the Hamiltonian is real analytic. And also that these two components, so we want properties in the critical level so that we can say something about the level is slightly above 0. So we assume that this critical level, it has these two components here. Both of them are strictly convex. So So this is a geometric property which makes sense in R4, which means the following. Each one of them is, let's say, they are strictly convex, means that each one of them bound a convex set, and also the curvatures at the regular points, the sectional curvatures are all positive. So these are the hypotheses. Then, for all energies slightly above 0, WE, which is something which looks something like that, admits a 3-to-3 foliation. Then I have to explain what that means. So a 3-to-3 foliation is the following. It's a singular foliation of the energy level of this guy here. It's a singular foliation, so that the singular set of this foliation is formed by 3 periodic orbits. And in the complement of these 3 periodic orbits, you have a smooth foliation of the energy level. So, and this foliation includes the Lyapunov orbit here in the neck, and also include these 2 hemispheres as regular leaves. So I'll draw a section of this foliation. So this is the belt sphere in the neck, just a section. So here is this orbit that we call P2, because it has index 2, Collisander index 2. So here are the hemispheres, those ones. This is slice, so we can imagine this figure by rotating around this axis. There is another periodic orbit inside, which we call P3, which is unknotted and has Collisander index 3. There is a cylinder connecting P3 to P2. We can see this cylinder, like this annulus around here. And in the complement here, inside this 3 ball, we see a family of planes foliating. all of them asymptotic to P3. And in the other side is exactly the same thing. So in the other side of this 3 ball, so here is another 3 ball, we would find this other periodic orb P3 prime here with a cylinder connecting to P2, and this family of planes foliating the rest. So this is what we call 3-to-3 foliation. The index of P3 prime is also equal to 3. So this is a better picture of this foliation. And here we have some examples, some applications of this. So the hypothesis is the convexity of the critical level. And we have to check this convexity. It's something that it's possible, it's not so difficult to be done when the Hamiltonian is of the form kinetic plus potential. This theorem holds for any Hamiltonian, but it's much easier to check this convexity property of the critical level when it has this form, kinetic plus potential. In this example, so the convexity is equivalent to the following. We have the projection in the position plane, x1, x2, of the energy level. And if we consider that function is square root of E minus V, it is non-negative inside the projection. So the convexity property is equivalent to checking that this function here is strictly concave. And moreover, the boundary of the energy level must also be convex as a curve. So this is an example that we can compute. There are many other examples. This is a perturbation of the Anon-Hiles Hamiltonian. Here we see the perturbation is in this term here. That the Anon-Hiles, this term is equal to 1. We take something slightly, can be any number between 0 and 1. So in this case, we see that there is the connected sum with a bounded component, with an unbounded component. And in this case, what we have is just one side of this foliation. So for energy positive here, we have this 3 ball separated by the belt sphere, and inside this region, we obtain this foliation. In the unbounded component, we don't know too much about that. So there are many examples in the literature. We found some funny names, but with Hamiltonians that we can work, like buckled nanobeam, nanotechnology. This other strange name here in chemistry. Also we can check that this, and also this other Hamiltonian in celestial mechanics. We can check that all of them satisfy, they have one of these pictures, the critical set. Maybe one of the sides is unbounded, but the convexity property can be checked for all these examples. I will talk about that. I will talk about this. In fact, this is the motivation for, not exactly the three-body problem, but I will talk about a simpler version of the three-body problem. But I can say something about the three-body problem. So, of course, this is only possible because we work with holomorphic curves. So we go to the symplectization. All these sets here, when we assume these convexity properties, not only below when you have these two components here, but at the critical level and above the critical level, all these sets have contact type, and the Hamiltonian flow is equivalent to a Hebb flow. And so we can use all this machinery from holomorphic curves to study dynamics and to produce this foliation. So the basic definition, so at this point we start we try to generalize this theorem. So I have to introduce this language of Hebb flows. We have a contact form on a three-manifold. It determines this Hebb vector field, determines this, the contact structure given by the kernel of the contact form. And the usual examples, which essentially are the ones that we have in this theorem, is the three-sphere inside R4. If we consider the Liouville form inside R4 with this QP coordinates, then if we restricted this one form to the three-sphere, it's a contact form producing the Hopf vibration. And, but we can consider functions, smooth functions multiplying this contact form to study other Hamiltonian flows on a general star-shaped hypersurface in R4. And moreover, for instance, if we multiply by a function which is symmetric with respect to the antipodal map, so f of p is f of minus p, then we can also consider Hebb flows on RP3, which is the quotient of S3 by the action induced by the antipodal map. So this contact form descends to RP3, the contact structure descends to RP3, and so we may consider symmetric functions, which is equivalent to study Hebb flows on RP3 with this standard contact structure. So I would like to recall two theorems that will be useful for us in Hebb dynamics. This very important theorem by Hofer, Vysotsky, and Zehnder in 1998, which says the following. So for Hebb flows, we may define the Conley-Zehnder index, and we can extend the Conley-Zehnder index to degenerate paths. So that's the Conley-Zehnder index that I am using here, the one defined by Hofer, Vysotsky, and Zehnder. And we say that a contact form on the three-sphere is dynamically convex if the index is at least 3 for all periodic orbits. And this name is motivated by the fact that if the hypersurface, the star-shaped hypersurface in R4 is strictly convex, then it is, in particular, dynamically convex. And the theorem says that if the contact form is dynamically convex, then there is this open book decomposition adapted to the Hebb flow associated to the contact form, which means that there is this special orbit, P3, with index 3, and it spans this family of disks, this S1 family of disks, each one of them being a global surface of section. So together with Umberto, we essentially passed this theorem to the particular case of RP3. We used the same method to produce this foliation on RP3. And there is a similar definition what means dynamical convexity on RP3. We have to consider all. Now, P1 is not 0, so we consider only contractible periodic orbits, and we assume that all of them have Conley-Zehnder at least 3 with respect to the global trivialization of the contact structure that exists. So in the case that the Hebb flow on RP3 is dynamically convex, then we can also prove that there exists this open book decomposition with disk-like pages. Each page is a global surface of section. But now the picture is essentially the same, but we have, so all these to to being asymptotic to a simple periodic orbit, the asymptotic limit is the double cover of a periodic orbit, of a non-contractible periodic orbit. So, but the picture is the same, but we must have in mind here that each leaf is converging to the double cover of a periodic orbit, which has index 1. So in this case, the main difference here, because the index is 3 and because it's the double cover of a simple periodic orbit, the main difference to the previous theorem is that we can say here that the binding orbit is non-hyperbolic. So in the previous theorem, it's not known if we can construct the open book decomposition with non-hyperbolic binding orbit. But here it's, it's always possible. So, before I state the theorem that we are working, it's not yet a theorem, but maybe a conjecture. I have to say that now we consider connected sum of RP3, and the main reason for that is many problems in celestial mechanics, we have this situation. So those two components that collide here, components of the energy level, instead of being sphere-like, they are RP3-like components. So we will consider this situation. And moreover, I showed you many examples where we can compute the convexity of the critical level. But the critical level has, here is like a cone close to the singularity. So in some directions, the curvature is 0, is almost 0. So for many Hamiltonians, when we try to check the convexity, we lose because close by, there is no convexity here. We see a picture like that. Something which is not convex, but maybe far away it's convex, but here it's not convex. But still, nearby, even if it's not convex here, the index of this region here is very high. Even if it's not convex, this set here is still dynamically convex. So we try to extend our theorem to a setup where the critical set, each side is homeomorphic to RP3 and dynamically convex. Maybe not strictly convex, but dynamically convex, meaning that the index of all contractible orbits is at least 3. So again, we have this saddle center equilibrium point. And we consider this RP3 with singular points at the critical level. And we have this connected sum of RP3 for energy slightly above 0. And we also have to assume, for instance, we are in a symplectic manifold, considering all these energy levels, all of them must be of contact type. Because here, when you have convexity, it's automatic, almost automatic. But there, we have to assume that there is a Liouville vector field defined on a neighborhood of the critical set, which is transverse to each energy level at the regular points. So with all these hypotheses, what we try to prove is the following. If the critical level is dynamically convex, then for energy slightly above 0, you have that foliation. But again, so this foliation is a 3-to-3 foliation, but those orbits here inside this region here, so all these leaves here, they converge to the double cover of a simple periodic orbit there. So the main consequences of this foliation is the following. Why we we want that this foliation exists. It implies, in particular, that the flow has infinitely many periodic orbits, and moreover, this orbit here is hyperbolic. Sorry. And this foliation implies that there are infinitely many homoclinics to this hyperbolic orbit. So this could be one way to show that in the three-body problem there exists infinitely many homoclinics to the Lyapunov orbit near L1. But in the three-body problem, maybe I can say a little bit about that. It's a very hard problem. I will illustrate with this example of the Euler problem, which is a simplification of the three-body problem. I mean the circular, planar, restricted three-body problem. In the Euler problem, there are two masses. Here is the plane, and we have these two masses, mu and 1 minus mu, at those points minus 1, 0, and 1, 0. And there is the third body, which moves according to Newton's gravitational law. It is attracted by those two masses, which stay fixed. They don't move. They stay there, but the forces are given by Newton's gravitational law, and you study the motion of this body subjected to these two forces. It is a Hamiltonian system, and it has this form. So it's kinetic plus potential. Very simple form, kinetic plus potential. So let us look at the energy levels of this system. So in blue here we see the projection of an energy level with very low energy. So it has two components here. So if the trajectory has low energy, it's either it stays orbiting around this body here, moving around here, or around here. If you increase the energy, then these two guys touch each other. It is this orange region here, the projection, which includes also the blue one. And there is this equilibrium point, which is exactly the saddle center equilibrium point, okay, in this region here. And if you increase a little bit more the energy above some critical value, which depends on that parameter mu, the mass ratio, then the projection of the energy level, you see disconnected sum, and then you start to see trajectories moving from one side to the other. Okay. There are the Lyapunov orbits nearby, but the problem here is that some orbits around here, they collide with these guys here, the primaries. So the collision is very bad because, in fact, these energy levels, they are not compact. Does not fit in the setup that we have. So we have to regularize these collisions using, we consider here elliptic coordinates to regularize. So we change x and y by u and v in this way. And it regularizes both the collisions in both sides at the same time. And there is a relation between the momenta in these variables, the new variables, according to this equation here. So if we change coordinates, this is a symplectic change of coordinates, and produce a new Hamiltonian in this way, so we just replace these coordinates, which are symplectic, and we subtract c. This is a usual trick of regularization. And here we see that we have this bad denominator here, which is 0 at these points here. Now, in the new coordinates, we still have a bad denominator, but then we multiply the Hamiltonian by this denominator, and we obtain a new Hamiltonian, which now the energy is a parameter of the new Hamiltonian. And this new Hamiltonian, it's almost like a miracle, decouples. It can be seen as the sum of two 1 degree of freedom Hamiltonians. This one, which depends only on U and PU, and this other one depends on V and PV. So it's a very simple integral system. So when we look at what's happening now, because there is this coordinates is not 1, 1. It is essentially 2 to 1. Now the new Hamiltonian is smooth. There is no more collisions, nothing here. And for energies below the first, the critical value, the energy level projects in these two components, which are in yellow here. Okay? But in this coordinate V, we see that this coordinate V is periodic. Okay, so I just consider one period. So the energy level projects here. Then in the orange, it touches. There is this is the critical value. The projection includes also the yellow one, and when you are slightly above, then it's the green one, including all the others. Okay. In this picture, there is a natural identification, because this is a 2-to-1 cover. In this component, at least, that if you take like antipodal points here, they go to the same point in the original coordinates. Each vertical slice here is a 2-sphere. So this is in fact an S2. If we consider only, if we identify these two sides here, this is an S2 cross S1. And there is a natural double cover of this S2 cross S1 to the connected sum of two copies of RP3. This is what's happening. We can see this in this picture. There is a nice way to fold this set to the connected sum of RP3 with RP3. So we are in this situation. This is the critical set here. And if we want to apply our theorem, we have to check that the critical set is dynamically convex. So in fact, this is not so difficult to check, because the flow decouples, so you can compute the index of all periodic orbits very easily. It is on the three-sphere. On the three-sphere, dynamically convex means that all periodic orbits have Conley-Zender index at least 3. On RP3, so some orbits are non-contractible. P1 is E2. So dynamically convex means that all contractible periodic orbits have Conley-Zender index at least 3. This is the definition. For the critical set, this is RP3 with the singular point. The definition is the same. All contractible periodic orbits in the critical set have Conley-Zender index at least 3. So the definition is essentially the same when you have this singularity. Yeah, there are two ways to check the dynamical convexity. Either we check that this, well, there are other ways. It's not only two ways, but we can check, for instance, that this region, the orange one, the energy level which projects here in the orange one, is convex, strictly convex. If we check that, then we know that it's dynamically convex. It's a geometric way of checking. In some cases, it's possible to do that. But then, in some other case, we have that problem that close to the singular point, you lose convexity. Then, in such case, you cannot use this criterion. And another way, which is the way we use here, is to use the fact that the Hamiltonian decouples in these two components here. So in this way, the behavior in the plane UPU and VPV is independent. And the Conley-Zender index is essentially the sum of the two components. There are other ways to check, but these are what we do to check dynamical convexity. So, yeah. So in fact, not with this regularization, I think, right? Using another regularization, there is a student, a student of Urs, Kim, right? Kim. He also checked that these energy levels are dynamically convex. Maybe, I don't know if up to the critical level or not, but I think it would work anyway up to the critical level. Yeah, but I think it's a different way. It's like considering families of orbits, right? Yeah, here it's, I just forget. I knew that there was a third way to check, and I was going to say that, but then I forgot. So in the Euler problem for energies, in fact, it's not just slightly above zero. It's for all energies, I think. But at least for energies slightly above the critical value, you have this 3-to-3 foliation. Although the system is integrable, not too complicated, it's a different structure to study the flow there. Just one comment about the three-body problem, right? The three-body problem is exactly this. In this setup, you have this RP3 connected some RP3. So to obtain this foliation, you have to check this dynamical convexity of the critical level. This is something very hard. The three-body problem, the only difference of the Hamiltonian is the magnetic term. But this makes a lot of difference. The hope is that for some small values of parameter mu, there is also a parameter there. In one side, because there are two sides, near the light primary and near the heavy primary. Near the heavy primary, in the limit, this critical set goes to the critical set of the rotating Kepler problem, which is dynamically convex. So maybe, I don't know, perturbing a little bit, still dynamically convex. I haven't checked that, but maybe. And in the other side, near the light primary, the critical set goes to the critical set of the Hughes lunar problem. Then it's much more difficult. I don't know if that will be possible to apply this result to obtain this foliation. Both sides, they behave essentially independently. You can show that there exists a foliation in one side, maybe not in the other side. But what is expected is that this picture holds in the three-body problem as well. It's just a problem of checking this dynamical convexity property. Sorry, I couldn't understand. No, I think for all. For all values of the parameter mu, you would have that slightly above the first Lagrange value, it would hold, this foliation should exist. In fact, I made a few numerical experiments, and in some cases it seems to be strictly convex. But when you lose this convexity, still you lose in a part where the index is very high, so it should be still dynamically convex. So probably this is the picture that is happening in the three-body problem. Otto von Kurt knows a lot about these numerical simulations, and I think that he confirms that, right? Yeah. Yeah. And so the idea of the proof, well, we have to produce this foliation. And we use holomorphic curves in the symplectization of the tree manifold. So there are three main steps. Find the rigid planes. Well, essentially, then finding this binding orbit is already there. We have to find these orbits, P3 and P3 prime, on both sides, and then we find this family of planes which behave well. They break in these cylinders, and nothing else occurs. So the rigid planes asymptotic to P2, they are almost there. In fact, it's very easy to find because we consider holomorphic curves, so we have to check essentially that these guys here, this belt sphere, can be made holomorphic for a special choice of almost complex structure. So the usual thing, so using holomorphic curves, the setup is always the same. We choose the one which sends the R direction to the half vector field, preserves the contact structure in the symplectization, compatible derivative of the contact form, and consider these holomorphic maps from Riemann surface to this almost complex manifold with finite energy. And we study the space of these holomorphic curves in the symplectization, and we expect that when we project them to the tree manifold, then it will produce a foliation like that. So, so the belt sphere, which would be the first step, we have to choose special almost complex structure. In fact, J in the contact structure, in such a way that these two guys here, they became holomorphic planes. And this is not difficult because we have a lot of symmetries using local coordinates, and we can solve almost explicitly and find these holomorphic planes. So this is not the difficult part. And also the action of this orbit is very small. Even if we perturb the data, they still exist. So the problem is to find the binding orbits. So how do we find that these guys exist? I will only consider this in one side. Just consider P3. So we have this situation, let's say like that here. And there is an estimate of the Conley-Zender index, which says essentially the following. Everything which is passing near the singular point, the index is very high. So this is essentially we can see from these coordinates that, for instance, so in these coordinates, the flow here is a saddle, but the closer you are to a trajectory going to the critical point, so the longer you stay near here. But then if you look at this plane here, this keeps rotating with essentially the same speed. Keeps rotating and rotating. But here you see that it gets very, a lot of time here. And essentially the linearized flow in the transverse direction of a trajectory can be seen by this plane here. So it keeps rotating. And this means that the Collinsender index gets very high for every trajectory which is passing close to the critical point. So what we do, we choose a bump function to take the energy levels slightly above, a bump function which is supported near the critical point, in such a way that they are deformed and you deconnect the back, but preserving the rest of the component. You just perturb a little bit here. So we can show that, so this part here, since the critical level is dynamically convex, when you perturb a little bit, it is still dynamically convex up to some high action, as high as you want. So when you perturb this, these two guys are now RP3. And they are dynamically convex up to some very high action. And so that previous theorem with Umberto for RP3, dynamically convex RP3, it still holds if it's dynamically convex with very high action, up to high action. So there exists the open book decomposition. That open book decomposition has this orbit P3 as a binding orbit with index 3. But the problem is that we made some surgery here, and we don't want that this orbit intersects this region, so that we don't have anything. But then, since this guy has index 3, and the action here we can control, it's uniformly bounded, it cannot touch this region here, because anything which touches this region either has very high index or very high action. So it must be away from this region here. So it is, in fact, this guy is, in fact, in the other side is the same thing. It is in the original energy level above. So the binding is there, is already there. It has index 3, the double cover. So now we can do Bishop family, like start to produce these planes, these holomorphic planes out of holomorphic disks. And the belt sphere might be an obstruction to produce the plane, but every time this holomorphic sphere break in the belt sphere, we glue with the opposite hemisphere and we continue the family. So some other problems might appear that this family could break in another orbit, which could be hiding in the homoclinic, in a homoclinic to the critical. And but again, if this homoclinic really exists and it's hiding some bad orbits which would prevent that plane to exist, this homoclinic for energy slightly above 0, we can prove that these orbits should be linked to this one. And all the problems that may appear are with orbits which are not linked. So even in the case we have a homoclinic here, the homoclinic should be linked. These orbits which are hiding here, they should be linked to this binding orbit, so they do not prevent the existence of this plane. So the rest is just compactness theorem to produce the foliation, and this cylinder here also must show up. So I should comment here that this foliation is very similar to the foliation that Richard Sifrin and Joel Fish studied, and connected sum of foliations. The picture is essentially the same. And I think that's it. Thank you.